This is the 13th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video discusses how to determine the time of a circuit, either the propagation delay of a single circuit or the growth function of time of a family of circuits like a ripple carry adder. In the previous video, we learned that a circuit or gate's propagation delay is the time it takes for that circuit to completely process a change to its input. Or in other words, it's the time that elapses between the last change to the input and when the output is guaranteed to have its final value. Each gate in a circuit has its own propagation delay that's determined by a number of things, including the size and type of the transistors and how those transistors are organized. When you chain gates together, you simply add the propagation delays. Here, each gate has a 10 nanosecond delay, so the total propagation delay is 20 nanoseconds. When input A changes, we must wait 10 nanoseconds before we're sure that the output of the OR gate is done changing. And then because in the worst case, that OR gate could have changed its output at time like 9.99999, we must wait another 10 nanoseconds to make sure the output of the AND gate is then stable. However, calculating a circuit's propagation delay isn't as simple as just adding up the delay of each gate. Consider this example. Notice that the OR gate and the NOR gate can run in parallel. Therefore, this circuit has a total propagation delay of 20 nanoseconds. At the end of the first 10 nanoseconds, both the OR gate and the NOR gate are guaranteed to have a stable output, so we just need to wait the additional 10 nanoseconds for the AND gate. A circuit's propagation delay is determined by its critical path, that is, the slowest path from any input to the output. This circuit has two critical paths, both shown in red. These two paths have a delay of 20 nanoseconds. The other two paths that are still in blue have a delay of only 15 nanoseconds. Now pause the video and find this circuit's critical path and propagation delay. The critical path, shown in red, has a propagation delay of 35 nanoseconds. Now let's consider the running time of the ripple carry adder. We begin by finding the propagation delay of the component full adders. Notice that the delay for the 3-input OR gate is longer than that of the 2-input gates. Pause the video and find the critical path and propagation delay for just this full adder. So for this circuit, the delay is 20 for the sum output and 25 for the carry out. So yes, each output can have a different delay depending on the path leading to that particular output. Okay, so here's a challenge to work on before the next class. How can you redesign this full adder to reduce the delay of the carry out? The trick, of course, is to avoid using the slower 3-input gate. But in order to do that, you may have to increase the delay on the sum. One of the upcoming homework problems will demonstrate how that trade-off between the time of the sum and the time of the carry out can be used to reduce the time of the ripple carry adder overall. All right, so given these delays for the full adder, what's the total propagation delay for the entire ripple carry adder? Pause the video and see what you come up with. Remember, the key idea is that the carries ripple across the circuit. 25 nanoseconds after the external inputs change, the carryout from the rightmost full adder is ready. And so is the least significant sum bit. But that's typically not useful because the rest of the sum bits aren't ready. Anyway, because that carryout is an input to the next full adder, as soon as it changes, we have to wait another 25 nanoseconds for the carryout for the second adder to be ready, which means it's not ready until 50 nanoseconds after the external inputs change. The third carryout is ready another 25 nanoseconds after that, and then the fourth, fifth, sixth, and so on. The seventh carryout is ready at time 175, and finally, the last carryout is ready 200 nanoseconds after the external inputs change. Notice also that the most significant output bit is ready at time 195, 20 nanoseconds after the seventh carryout bit is ready. Now, it's important to know the precise propagation delay of this circuit so it can be correctly incorporated into larger circuits like ALUs and CPUs. But that doesn't answer the higher level question we asked at the end of the last video. Is the ripple carry adder overall a good design? Or is there a better approach to designing an adder? So to answer this question, we need a way of comparing designs, not just specific implementations for a given input size. Think about how we compare algorithms. In particular, think back to CIS 163 and how you compared sorting algorithms independently of the programming language used or the specific array being sorted. Remember, you looked at how the graph of execution time grew as the size of the input array increased. For example, this graph shows that the time needed for a selection sort increases much more rapidly than the time needed for a quick sort. Not only that, but the graphs are fundamentally different shapes. The graph for a selection sort is a parabola, whereas the graph for quick sort is nearly, but not quite, a line. We formalize these differences by describing them using a type big O analysis. Selection sort is big O of n squared, whereas quick sort is big O of n log n. So using this idea as a model, let's do a big O analysis on the propagation delay of a ripple carry adder. How rapidly does the propagation delay increase as we add input bits? Well, we can see from the yellow boxes that each additional full adder adds 25 nanoseconds to the total propagation delay. Thus, the ripple carry adder's total propagation delay is approximately 25 nanoseconds per input bit, which means that the running time of this ripple carry adder is big O of n, or linear. We may be able to make some minor incremental improvements by modifying the full adders, but a significant improvement requires a different design. Now, just for point of comparison, what's the big O propagation delay of a circuit built using the big hammer? Would using this brute force technique result in a much faster adder? Well, let's see. Let's start by looking at the is prime circuit from video 1. So this is a typical circuit built using the big hammer with 3 input bits. How long is the critical path here? And to keep things simple throughout the rest of this video, let's just treat the propagation delay of all gates as 1. All right, here is one of many paths that go through exactly 3 gates. In fact, notice that all of the paths either go through 2 or 3 gates. All paths go through one AND gate and the OR gate, and some paths also go through one NOT gate. So with that in mind, how does the critical path change when we apply the same approach to a truth table that uses 5 inputs? Just as before, all the paths go through either 2 or 3 gates. Well, that doesn't seem right. Does that mean the time for a circuit designed using brute force doesn't depend on the number of inputs? Well, no, of course not. So look closely and see if you can figure out what will make this circuit have a longer propagation delay than the 3 input is prime circuit. Okay, here's the key. Notice that as the number of inputs to the circuit increases, the number of inputs to the AND and OR gates also increase. Specifically, these AND gates all have 5 inputs, 1 for each bit of input to the circuit. OR gates have 1 input for each row in the truth table that contains a 1, which could be as big as 2 to the n. Clearly, a 5-input gate should be at least somewhat slower than a 3-input gate. So how do we account for this when doing a big O analysis? Well, there are several possible models, but to keep things simple, we're just going to require that all gates be 2-input gates. So then the question becomes, how do we build an n-input AND gate using just a bunch of 2-input AND gates? Try it and see what you come up with. One approach is to build a tree of AND gates, kind of like a tournament bracket. Notice that if all the inputs are 1, then the output of every AND gate, including the output of the entire circuit, will also be 1. But if any input is a 0, then all the gates on the path past that 0, up to and including the output, will be 0. This is precisely the behavior that an AND gate should have. It is only true when all of the inputs are true. So then, using this pattern, how does the propagation delay of an n-input AND gate compare to that of a 2-input AND gate? The key observation, of course, is that the time depends on the height of the tree. So let's look at the pattern. Every time the height of the tree increases, the number of possible inputs doubles. Thus, the number of inputs is exponential in the height of the tree. If the height of the tree is n, then the number of possible inputs is 2 to the n. Now what we really need to know is the opposite. Given the number of inputs, what's the height of the tree? So we just take the inverse of 2 to the n, and we see that the depth of the tree is the log of the number of inputs. Therefore, we can count the propagation delay of an n input gate as big O of log n. So now let's analyze that 5 input circuit again. The set of NOT gates all run in parallel, and they each just take 1 gate delay because they only have 1 input. So we can call that a constant amount of time, big O of 1. The set of AND gates also run in parallel. Each AND gate has n inputs, so this entire bank of AND gates takes a time that's big O of log n. Finally, the OR gate has 2 to the n inputs, so its time is big O of the log of 2 to the n. Now, because these two operations, 2 to the n and log n, are just inverses, this simplifies to big O of n. These 3 stages happen in sequence, so to get the total propagation delay, we just add them together, which gives us an overall propagation delay that's big O of n. This is true of any circuit designed using that sum of products big hammer technique. So if we were to use that technique to design an adder, it would also have a running time that's linear. Now whether that would be faster or slower, the big O doesn't tell us, but it does tell us that the time would increase at about the same rate as we added input bits. So from that perspective, the ripple carry adder is not looking too bad, but it turns out we can actually do better, and we'll see that in video 15. Okay, let's summarize. A circuit's propagation delay is not just the sum of the delays of its components, because some of those components may execute in parallel. So to compute the propagation delay of a circuit, you have to look for its critical path, which is the path through the circuit with the longest total delay. When doing a rigorous big O analysis of a design pattern like a ripple carry adder, you have to remember that n input gates are slower than 2 input gates. And one way of accounting for this is to assume that any n input gate is a tree of 2 input gates. And any trees built in this manner have a propagation delay that's big O of log n. But remember, building gates out of trees and counting them that way is only necessary if you're doing a big O analysis on a design pattern. If you're just trying to find the propagation delay of a single given circuit, then you just find the critical path and add up the times of the components. Each gate should have its own specific time that already accounts for the number of inputs. Now, when doing a big O analysis using that tree approach, the ripple carry adder has a time that's big O of n, as do circuits designed directly from a truth table sum of products. Now, based on this video, I might ask you to examine a circuit and find its critical path. And then I'm likely to also ask you to compute the propagation delay for that circuit. I may also give you a design pattern for a series of circuits with increasing inputs and have you describe how the time for those circuits increases using big O. In the next video, we'll apply these same techniques to analyzing the size of circuits.